In this problem, we're given a heavy disk. We have a mass of 2.2 kilograms on this, and we're told the diameter is 28 centimeters, which means, of course, that the radius is 14 centimeters. And this thing is mounted on an electric motor. We're told the motor produces an average power of 42 watts for a time of 6 seconds. So before we even read deeper into the problem, what that gives me is the total energy input into the disk, because I can take the power and multiply it by the time that power acts for, and I'll get the total energy transfer into the disk. And I'll go ahead and just write that down immediately. Delta E, so the energy input into the disk is just power times the amount of time that's gone by. That's 42 watts, which is 42 joules per second, times 6 seconds. And this gives me 252 joules of energy input. All right, finally in the setup for the problem, we're reminded that the moment of inertia of a disk is given by 1/2 mr squared. And now we can get into the different parts of the problem. So in part A, I want the final angular velocity of the disk. Well, I know that 252 joules of energy has been pumped into it. And where is that energy? It's in the rotational kinetic energy of the disk. That rotational kinetic energy is given by 1/2 I omega squared. So it's useful, before we plug all the numbers in, to just calculate the moment of inertia of this disk separately. Again, that's 1/2 mr squared. We plug in the mass of the disk. We plug in the radius in SI units, so this is 0.14 meters squared. This gives me 0.02156 kilogram meters squared. So now if I go up and do my energy calculation, I have a total rotational energy in the final state here of 252 joules. That's equal to 1/2 times the moment of inertia, 0.02156, times my final angular velocity squared. And we can solve for omega, and I get 153 radians per second. Now in part B, we get into some of the angular kinematics that's going on with this disk. So I want to get the average angular acceleration. Well, that's just the change in angular velocity divided by the change in time. So delta omega over delta t. Because my initial angular velocity was 0, my change is 153 radians per second. The time for the acceleration process, again, was 6 seconds. And this gives me 25.5 radians per second, or radians per second squared. Now that I have the average angular acceleration, I can get into part C. I want to get the average torque exerted by this motor. And we remember the rotational version of Newton's second law, tau equals I alpha. We're averaging over this 6 second period, so we really should say tau bar for the average torque and alpha bar for the average angular acceleration. In our moment of inertia, we plug in 0.02156. In our average angular acceleration, 25.5. And to 3 significant digits, we get 0.550. And the units there are Newton meters. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.